In this video, we're going to be going over equivalent resistance and how to find the equivalent resistance when you're given a circuit with multiple resistors. So when we are analyzing a circuit with multiple resistors, you have to be very methodical and just do each little piece. Like for example, we're going to do this piece first, and we're going to find the equivalent resistance, and then we're going to take that equivalent resistance and make that a part of a new circuit that we'll draw, which is still the same circuit, but it's going to be a condensed version, a more simpler, manageable version of our previous circuit, and so on and so on and so on. And eventually we'll have the equivalent resistance of the entire thing. Now, real quick, equivalent resistance is just saying, like, if I want to know, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 resistors in this ladder of resistors. So if I wanted to have only one resistor, what would that resistor's resistance, a lot of resistance, have to be equivalent to equal the resistance that was provided by all of these 9 resistors, if that makes sense. I hope that was clear. Okay, so let's get started. So we have these 3 resistors right here that are in series. Now, how you can tell if it's in series is if I had current going right here, it doesn't have a choice. Now, when you get here, it has choices. I can go there, there. But when we break it up into these little manageable sections, there's only one option for current to flow through. If you see current having a choice, you know that it's in parallel, and we'll get to that in a second. Okay, so when you add resistors in series, you just add them linearly, so we R plus R plus R, which is going to give us, you guessed it, 3R. So this is our equivalent resistance, which I'm going to label and I'll show you. This is our equivalent resistance 1, which I'm just going to call REQ1. All right, so then we have to redraw our circuit. Oh, I should probably put the resistor in there. And you do need to redraw this every single time, but you'll see why in a second. So we just had 3 right there. Now we only have this 1. This is REQ1. Now this is much easier to deal with, right? So now we just have these 2. We're looking at it piece by piece by piece. All right. So now these are in parallel. So if I had current flowing, along here, it could go, this way or that way. It has choices. And so this is what we would call parallel. And so when you're adding in parallel, you're going to be adding the reciprocals, which this is still R, a value of R, plus it would be 1 over REQ1, because it's the reciprocal of that equivalence that we just found. Now you have to make sure you take the reciprocal of the sum of the reciprocals. Okay, it's a mouthful. All right, so what we have here is 1 over R plus 1 over 3R. Make sure you carry that -1 all the way through until you get to the end, because if you miss one little part, then that changes your answer for the next piece and the next piece and the next piece, and then you get to the end and you have the wrong answer. Now that's also why it's really, really important to show all of your work. When you're going through and you're doing this and you're redrawing it, a lot of times your professor will see, okay, well, they had the right idea, they understood the concept, but say they forgot to take a reciprocal. And I guarantee you, you're going to be getting some, a whole lot more partial credit than if you didn't show this. Okay, so moving on. So now we have 1 over R, 3 over 3, this 1 over 3R. And I'm doing this to get a common denominator. So then we have 3 over 3R, because we need that if we're going to be adding. let me keep this -1 plus 1 over 3r. And I can multiply by 3 over 3 because it's equivalent to 1, so multiplying by 1 doesn't change anything. So then we have 4 over 3r, which I still need to take the reciprocal of, which is going to give us an equivalent resistance of 3 over 4r for our equivalent resistance 2. That should be a Q, not a G. Okay. Now, you guessed it, we're going to redraw our circuit. So we're going to go like this. And then this is going to be our REQ2. Now, we're going to take these 3 pieces right here, just like we did in the beginning, and we're going to add these. Well, now we're dealing with series. So we have R plus REQ2. So R, because remember these are all still a value of R. And that equals 2R plus REQ2 was 3R over 4. We need a common denominator, so we're going to multiply by 4 over 4. And that will give us 8R over 4 plus 3R over 4, which gives us 11R over 4 for our equivalent resistance. Now we're on 3. All right, so we're going to redraw our circuit. Oops. Okay, so this is REQ3. So we just condensed, we took these 3 and we combined it into 1, which is now going to be in parallel with this one that also still has a value of R. So now we're going to say we have to take the sum of the reciprocals, take the reciprocal of the sum of the reciprocals, plus 1 over REQ3, which is going to be R plus 11, oh, we got to take the reciprocal of that, so it'll be 4 over 11R. And when you're taking the reciprocal, you're just flipping this over. Okay, which is then going to equal, we need to get us a common denominator, so let's multiply by 11 over 11. I'll show that. Which is going to equal 11R over 11 plus 4R over 11. We have to take the reciprocal. That's going to give us 15R over 11, which equals 11 over 15R. And this is our equivalent resistance 4. Now we need to redraw our circuit. So we're going to go like this. And now you just have this. This is going to be our REQ4. And these are still with a value of R. And now we're just going to add these, our last piece. And they're all in series, so it's just going to be R plus REQ4, which is going to equal 2R plus 11 over 15R. Have to get our common denominator here, so we're going to multiply by 15 over 15, so 30 plus 11 is 41R over 15. And this is REQ5. So to get our total the equivalent resistance. We plug in our value that we know for R. Remember, it was up here. They are equal 175 ohm resistors. So we're going to plug that in. Whoops. Somehow we got quite a bit of space in there. Okay. So we will say 4115 times 175. Plug that into the calculator. And we get that our equivalent resistance is 478.33 ohms, which ends up, you could round that to 478 ohms because we were given 3 significant figures. And that is how you calculate equivalent resistance. And we'll do some more practice. Okay, so we have this problem here that says, what is the net resistance of the circuit connected to the battery? And these all are going to have a value of R. Now this I have flipped upside down. So this is the same resistor circuit as up here. I just think it's easier to see pieces, so to speak, this way, but you could keep it horizontal if you'd like, but I like this way. So we're going to do it this way. Okay, so we have resistor R, on and on. Okay, so again, we need to be very methodical. We need to take it piece by piece and find the equivalent resistance and then add that to the next piece that we're taking a section of, so on and so on. So we're going to start with these two. So we have these two that are in series. This is going to be R plus R equals 2R. So this is going to be our equivalent resistance 1. Okay, now we need to redraw our circuit. So now we're going to have as long as it has the same pieces in there. It doesn't have to be, you know, exactly like that, but you need to have a general idea. So now this is going to be REQ1, which we know is 2R. So now we're going to take these two, and we're going to add them together, and they're in parallel. So we're going to add those together, and that is going to be REQ1 plus R. But remember, since they're in parallel, we have to take the reciprocal. So it'll be 1 over REQ1 plus 1 over R, and taking the reciprocal of that. So 1 over 2R plus 1 over R. So we're going to have, let's go ahead and get a common denominator. 2 over 2, so that'll be 1 over 2R plus 2 over 2R, and that would be 3 over 2R, but we still have to take the reciprocal, so it's going to be 2 over 3R, and this is going to be our equivalent resistance 2. Okay, so let's redraw our circuit. So this is going to be our first analysis, and then we're going to, well, technically this is our first analysis, but this is our first input of that. So then we'll say this is our second analysis. Now let's do our third. Okay, so we're going to redraw our circuit now. Okay. So now we're going to analyze this part. And this part right here is REQ2, which we know equals 2/3 R. And so we're going to be adding these. These are going to be in series. And so this is still a value of R. So we have R plus REQ2. And so we know that R is just R, but we have REQ2, which is 2/3 R. And so we need to get a common denominator. So then we're going to have 3/3R plus 2/3R equals 5/3R. And this is going to be our equivalent resistance 3. Or we could say our equivalent resistance from our third analysis. Okay, and so then we're going to redraw our circuit. See what we get from our fourth analysis. Okay, so R, EQ3. Let me do that in red. Okay, and then we have this value of R. So now we're going to take care of these two pieces. And so we have, these are in parallel, so it's going to be 1/REQ3 plus 1/R, taking the reciprocal of that. So we have 3/5R plus 1/R equals, we have to get a common denominator, so multiplying by 5/5, that gives us 3R/5 plus 5/5R, and that's going to be 8R/5. Don't forget to take your reciprocal, which leaves us with 5/8R for our R equivalent 4. Okay, and then let's redraw our circuit for our fifth analysis, and we're going to have, so we've gotten rid of this portion, and now we're left with a portion that is equal to the two of those, is equivalent. That's what equivalent means, equal. And so now we're down to a very manageable chunk, which is going to be just these two. And we are going to then add these, which this one has an equivalent resistance of 5/8 R, and this one has a resistance of R. So we're going to add these linearly. So R plus 5/8 R equals, so we need to get a common denominator. So we're going to have 8R/8 plus 5/8 R equals 13R8. And this is our equivalent resistance, 5. But because we aren't given another value for R, this is also going to be our equivalent resistance total. Resistance, there we go, which you can just write as REQ. Now that we've found that, the total equivalent resistance for the entire circuit, let's do another for practice. Okay, I think this is a good problem to show because if you look at this and we just want to determine the equivalent resistance, which I wrote twice, equivalent resistance of the circuit, then you know that for series, all we do is we add the resistances, so R1 plus R2, etc., etc. But for resistors in parallel, we do 1 over. So we take the sum of the reciprocals, and we take the reciprocal of the sum, so etc., like that. So if we look at these, initially it may look like these three are in parallel, but they're not. And I want to explain why they're not. Maybe you caught that they're not, but just to be clear. So if you see right here, when the current comes out of this 12-volt battery and goes this way to the right, it only has one option. So if the current only has one option, then it's in series. It's not in parallel. Now, when the current comes out of the negative end, you're going to see that it has two options. It's going to go here, and then it can split off. And so this area is considered in parallel, whereas this area is considered to be in series. So now let's add them accordingly, since we've paid attention to that. So when current has a choice, it's in parallel. When it doesn't have a choice, it's in series. So we have 1 over 680 ohms plus 1 over 820 ohms. Then we have to take the reciprocal of that plus how we would add for series, 960 ohms equals, let's put that in our calculator, and I get 1331.733, and that's going to be repeating. Make sure you're checking how this goes in your calculator, because if you put it in certain ways in different calculators, you're not going to get the correct answer. So make sure you're practicing along with these problems, or trying to solve them on your own, or make sure you're using your calculator. Okay, let's do one more. Okay, I like this problem because it shows how some things might come in handy if you're using this in the real world. So this problem says, a close inspection of an electric circuit reveals that a 480 ohm resistor was inadvertently soldered in the place where a 350 ohm resistor is needed. How can this be fixed without removing anything from the existing circuit? Well, because of our knowledge of circuits, right, and resistors now, we know that the resistance goes down in a circuit when you have resistors in parallel. So we know that we can add a resistor in parallel, and that will bring down our overall equivalent resistance throughout this circuit. But how do we figure out what is this supposed to be, right? So what we're going to do is we are going to use our, the way that we add equivalent resistances, and we're going to say, we'll call this R1 and we'll call this R2. So we know that right now in this circuit we have 1 over 480 ohms. Oh, this, can't forget that we have to take the inverse, plus 1 over R2. Okay, so what we're trying to solve for here is R2. And we need for our equivalent resistance, we need for our equivalent resistance to equal 350 ohms. So we'll move R2 over here. Actually, let's do this. 1 over R equivalent minus 1 over 480 equals 1 over R2. We still have to keep that around there. And remember, we want our R equivalent to be 350 ohms, so it'll be 1 over 350 minus 1 over 480 equals 1 over R2. And we don't want to know the inverse of R2, so we can just make this just R2. Okay, so let's put that in the calculator. And I get 1292.307 ohms. So to 2 sig figs, that would be 1300 ohms is what we would need to put in right here to have an overall equivalent resistance of 350 ohms. All right, I hope this was helpful. Keep practicing.